Back. It's been a week. Hopefully it was a good one for you. It was good for me, and nice and restful. We are going to proceed into the next unit, and as usual, a problem. So max value. Okay, so you have a collection of balls 1 through 20. I've got the balls 1 through 9 up here as a sort of a visualization. Anyway, balls number 1 through 20. You select 3 without repetition. So select 3 without repetition. Here are 3. Maybe it's like these 3, and you take the max. Okay, so the topic today and for the next little while is going to be something called a random variable, and I'll go through all the definitions about that in a moment, but we don't need the definitions to solve the problem. We can just solve it using combinatorics as always. But anyway, m essentially carries the max, okay, so it's the max of those 3 numbers. So we have this notation now, compute the probability of m equals I. This is now an event, okay, but it's an equation, so this is the same thing as the probability that the max of the 3 balls is I. Okay, so it's a function of I. Okay, but anyway, we're going to have that notation very shortly, and it's a very handy notation. Probably you would have expected it to behave this way anyway. That's sort of what it is. Probability m is equal to I. Anyway, it's a probability problem. Okay, so compute the probability that m is equal to I. Okay, now there are a whole bunch of different selections available. I will do the the easy part, the denominator part of this. Okay, all of them are equally likely to select 3 of the 20 here. That's going to be in 20 choose 3 ways. Okay, so we'll select 3 of the 20 balls, and 20 choose 3 ways. Okay, so this is traditionally our size of our sample space. Everything is equally likely. Okay, each one of those is equally likely. So all we have to do is count the number of selections that has I as a maximum. Okay, how many ways are there? How are we doing? You're using independence. So probability. So you said probability that you pull I times the probability that you pull nothing greater than I. I don't know how to do. Like, I know how to do the probability of each of those. I don't think that they're independent. That's the problem. Yeah, probably best to avoid independence on this one. Yeah. I minus 1 times I minus 2. How'd you get that? Yep. Good. Yeah, so if you sort of think about the blanks as a collection of things, right? You're sort of saying I is here, right? And it's already been chosen. And then there are 2 blanks here, I minus 1 and I minus 2 choices for each of those, right? I think that's where you're going with that. This is pretty close. There's a problem with this this method, and it's just one small problem, but it's still a problem. What's the problem with doing it this way? No, no, I is the max. You're saying some of these could be greater than I. No, these are the possibilities for everything being less than I. That's not the problem. Right, yeah. So this has sort of an ordered feel to it, right? Sort of a permutation sort of feel, and this is not a permutation. Okay, so since we're doing one or the other, like, we have to stay consistent. Okay, so that's just the usual gotcha. If we're using combinations, which we're using here, we should use combinations over here. Okay, so instead of I minus 1 times I minus 2, this should be I minus 1 choose 2. Okay, but it's not far off. It's only off by a factor of 2. Okay, so if m is equal to I, it means while I is there, there's only one way to do that. Okay, it's like 1 choose 1. Okay, so there's one way. It's not very exciting. Along with 2 other balls less than I. And this is in I minus 2 choose, sorry, I minus 1 choose 2 ways, pardon me. Okay, so anyway, so it's 1 times this, which is just that. Okay, so the probability that max is I is the division of these 2 things. So I minus 1 choose 2 divided by 20 choose 3. Okay, well, this is slide 6, so we'll come back to this problem in a little bit. And there's some variations on this that are interesting for the discussion we're going to have. Yeah. If you graph this as a function of I, we're going to do this actually, because that's part of this random variable discussion is what does the graph of the probability look like. I minus 1 choose 2 as a function, if you multiply it out, it's a quadratic. It's I minus 1 times I minus 2 over 2, and that will expand into I squared over 2 essentially. So yeah, it'll be a parabola, or part of a parabola. Anyway. Okay, let's get to it. Okay, so this is packet 5. It's packet 5. Packet 5 is it's a short packet. It is the last packet that you're responsible for your midterm, which is on the 14th. There'll be little bits and pieces of it on assignment 4. But the main meat of the discussion is going to be about distributions and some of the metrics that we do. So it'll be just a little bit of stuff on your midterm, but not a lot. Anyway, let's just get a brief review of where we've been. Okay, so we've been talking about sample spaces and probability and all the other sorts of things that happen with set theory and probability. The most complex thing is conditional probability. Okay, so just changing the sample space by intersecting where it was with the new sample space. Okay, we're not going to talk about conditional probability for a little while. Okay, it's not that it's not important. It's just it's not going to be part of this random variable discussion very much. But this stuff is. Okay, so what is important? There's a probability function that maps outcomes in a sample space to probabilities such that the total of all those outcomes sums to 1. An event is any subset of the sample space. You add up the individual probabilities to get the probability of that event. And the last bit has to do with partition. I know we applied this to other things like law of total probability, and that's really important stuff. But again, we're not going to talk about conditioning for a little while. We're going to set that on the back burner. Just want to talk about what happens when you partition. Okay, so if you partition, it could be a k-way partition, the entire set, this entire sample space. All these are mutually exclusive, and each event, each possible outcome is in one of these things, exactly one of these things. The probability of this sums to the probability of the sample space, and we know that the probability of the sample space is the same thing as saying it's 1, right? Because it's the entire set. Okay, these are the important things that we're going to need going forward. And let's go forward. Okay, so what's a random variable? Well, to inform our discussion and do some the analysis that we want to do, oftentimes we're interested in just measuring one thing, okay, one thing about your experiment. And usually it's a numerical thing. It doesn't have to be, but for this course, it's always going to be. Okay, it's always a numerical thing. Okay, so that's the definition. Okay, so for a given sample space, a random variable simply is a function that maps everything in the outcome set. Okay, so everything from S to a real number. That's it. Okay, so I'm going to show you a few examples. We just saw one at the beginning of class, but we'll do coins and dice because they're familiar to us. Okay, so here's an example. We toss 3 fair coins and we define the function C that maps all the head-tail combinations. Okay, so head-tail strings of length 3, there are 8 of them, as follows: HHH3, HHT2, HTH2, HTT1, THH2, THT1, TTH1, and TTT0. Okay. As usual, there is nothing wrong with writing a function like this. This is an exhaustive method. Everything is accounted for in the domain, right? So, but we don't usually do this, right? Because maybe you're just trying to figure out a pattern, right? Maybe you can see a pattern in this random variable that might be an easier description. Maybe. Do you see a pattern? What's the pattern? Well, yeah, I was pointing out to him, but that's okay. Yeah, it's a number of heads, right? So you could summarize this thing and rewrite it as C is the random variable representing the number of heads, counting the number of heads. Okay, maybe that's fun, right? Maybe that's a nice puzzle to, I'm giving you a function and then you try to figure out what this function is, a nice words description, a very natural description. Okay, but typically this isn't done. Okay, so we typically don't do this. Okay, typically we start over here and we say C is the thing that counts the number of heads, and then we might derive this and draw pictures for this. Okay, we're going to see some other representations besides this exhaustive method. Okay, but usually it's some natural thing. Okay, some natural description, like counting the number of heads, or when we do the dice example on the next page, roll 2 standard dice and describe the random variable that takes their sum. Okay, so when we did the dice rolling thing, there were many different ways of writing out this sample space. The one I'm going to use today is ordered pairs. So 1, 2, 3, 4, 5, 6. Cross product 1, 2, 3, 4, 5, 6 for the second die, and that gives us an ordered pair list of 36 dice. 1, 1, 1, 2, 3. I don't have time to write them all out, so just let me know what's in here, right? Okay, so 36 things. The random variable R takes their sum. Okay, and it's interesting. We know what the sums are, right? It starts at smallest is 2, biggest is 12, any integer in between. Okay, so this random variable is mapping onto the integers, and again, I'll just use dot 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 because we know it's there. Okay, from 2 all the way up to 12. That's the range. Okay, so that's the part of the real number line that's in there, and it's a function, right? So you can take R of any of these die rolls, right? So R of 4, 5 is 9. R of 2, 2, it's 4. R of 6, 1 is 7. So you get the idea. Okay, so a couple of notes. Now that we've seen a couple of these things, and we'll do the max one again in a moment, that's another random variable, taking the max of 3 things. It's possible. First thing, random variable is perhaps not the best name, but everybody in the business calls it a random variable. It's a bad name for 2 reasons. One, it's not a variable, it's a function. Okay? So that's bad. And the other thing is it's not random. There's nothing random built in there. We're eventually going to talk about the probability function, and we're going to bring that into the discussion and see how that's tied to the range. Okay, but it's not random. Also, as a technical point, I mentioned this in the preamble, you can choose anything. Okay? You can choose any codomain that you wish, not just numbers, but numbers are the most interesting thing for us, and that's all we're going to use. Okay, so that's we're not going to mention this ever again. Okay, so always numbers, but if you read your textbook, it's going to tell you some things. Okay, so that's the definition. Let's go on. So how do we bring the probability of this thing into the discussion? Well, we associate the probability function to members of the range. Okay, so any collection of outcomes that map onto specific elements of the range, they're all taken as a block together. Okay, so all the, in the dice rolling example, it's like what are the outcomes that lead to an 8? Okay, so you collect them all together, and there are 5 of them. So that event space, this is defined as this, E sub x, where x is the element of the range, are all the elements in the sample space where the random variable maps onto x. Okay, so this is going to serve to partition the event space into blocks. Okay, so it's going to collect a whole bunch of outcomes together associated with. So for example, with the coin tossing thing, there can be 0 heads, there can be 3 heads, or anything in between. You can break it up into blocks like this, right? So here are all the ones where c equals 1. That's all the ones where c equals 0. This is all the ones where c equals 2, and this is all the ones where c equals 3. Okay, so the range, there are 4 elements in the range. You can sort of tag them by event. Okay, so the event such that you're going to get 2 heads. There are 3 possibilities there. And then you can ask yourself the question, what's the probability that c is equal to something? Okay, so let's do a quick example. Okay, so we can compute the probability that c is equal to x and treat that as an event. And I've listed it up here as e sub x. You can use e sub x if you want. Okay, but we like this notation. It's much more readable. So for example, the probability that c is equal to 2, that is equal to the probability of these 3 things collected as an event, as possibilities in the sample space. So HHT, HTH, and THH. And there are 3 out of 8 possible things, so we get 3 8s. Okay, so this is how the probability gets tied in. And as to the question earlier, we are going to eventually graph these things. Okay, so we're going to graph them over the range. So that's the next thing. Anyway, the range is therefore partitioning the, that's how it's defined actually. Okay, so the range is partitioning, so the entire sum over all those probabilities for everything that's in the range must equal 1. And that kind of makes sense, and as a quick proof, the sum of x in all range of R, the probability that R is equal to x, if we just transform this thing into this E block here, right, so it's all the sample space where you collect, where it gets to x, right? So this is x in range of R, the probability of E sub x. Okay, and those are events. Those are distinct events, and all of them, they sum to get you the entire sample space. They have to, right? Because everything maps onto something in R. Okay, so this stuff, right? This partitions S, and the property of partition is that it equals the probability of S, which is 1. Okay, so a very quick one-liner, but it follows that intuition that we have that everything's got to be covered. It's got to map somewhere. No problem. Okay, so just quickly going back to the first slide here. Okay, so for max value, okay, we're not doing anything fancy here. We're just using combinatorics. And again, nothing new. This is a generalization for m is equal to I. If we sub in all the possible values of I in here, and I guess what's the smallest one? 3. I guess 1, 2, 3 would give us a max of 3. Can't get any smaller than that. The max is 20, right? Any of the numbers in between. So if we summed up all this, we should get 1. Okay, so that's an interesting combinatorial proof that the sum of all that stuff equals 20. Choose 3. Okay, but that sort of follows our intuition, right? We try all the possible things in the random variable space, and we should get a total of 1. Okay. Next. Indicator random variables are special because they're domain, well, sorry, their range is 0, 1. Okay, so their range is 0, 1. Not their domain, yeah, so their range is 0, 1. And they're, yeah, and when does it map onto 1? It follows an event, okay? It follows an event E, and if E is, E occurs, then we get 1, and if E doesn't occur, then we get 0. Okay, so it's like a true-false Boolean sort of thing. These things are very, very useful. They simplify a lot of problems for us, and we'll see it down the line. And anyway, since it's 0 or 1, we can write out the probability that IE equals 1, right? It's the probability that the event occurs. And here it's 0, is the probability the event doesn't occur. That's another way of writing E bar. Okay, so you can use the complement rule for that. And that works too. This capital I is interesting. I didn't pick the font necessarily, maybe very well. Other textbooks make it much clearer that this is a capital I and not a 1. And sometimes they put scripty things on it, like, that would be sort of a standard sort of I to make it clear, or they do this sort of weird italicized E, I sub E. Anyway, so you'll see this in textbooks as well, so just so that you're aware. I'm just using this because it looks different than the ones that I have, so I think we're fine. But okay, so you'll see this, so see these in your textbooks. So just be aware of them. Okay, so let's go on with the max of 3 balls and do an indicator, okay? So with the random variable m as before, the h is the indicator that m is at least 19. So the max of 3 balls is at least 19. Okay, so what's the probability h is equal to 1? Okay, so that's sort of a very funny way of describing an event, m is greater than or equal to 19. Okay, but this event, we can just write it out. They're both the same thing. Right? So if we want to compute the probability h is equal to 1, this is equal to the probability that m is greater than or equal to 19 as that event. Okay, and it's event on a random variable. Okay, there's nothing complex about that, but it would be nice to figure out what this thing is now. Let's see what we've got here. Okay, so we have the probability that m is equal to I. Let's see, and there's 2 cases, right? Okay, that's a good way of doing it. So there are 2 cases, so maybe it's the probability that m is equal to 19, so that's one event, plus the probability that m is equal to 20, and then we can sub in those 2 formulas. Okay, so that's 18 choose 2, over 20 choose 3, and that's 19 choose 2, over 20 choose 3. So we'll just take a common denominator right away. And run this, oh, sorry, are we off the screen? Okay, just hold on one sec. And we run this through a calculator, and we got, let's see, we got 153 for this, and 171 for this, and 1140 for this. So it's 324, which is kind of a nice number, but it doesn't divide out everything that's in the denominator. Lots of common factors, but not all of them. This is around 28%. Which might surprise you, that this is fairly frequent, that you're going to get a 19 or a 20. That's the max on 3 20-sided dice. Okay, sorry, not 20-sided dice, sorry, a pull of 3 numbers out of 20. Yeah, so the question was, going back to the thing about being a misnomer, how is m a function or not a function? I mean, it is a function. So all we're doing is, so we're saying m is the max of 3 balls, right? Okay, so it's mapping the, whatever balls you're pulling out, it's mapping that onto a number. It's taking the max function. So it is a function, and this is just an inequality. So this is just describing an event. Okay, so you're just comparing the result of that function with 19. So there's nothing being computed like function-wise here. You're just asking the question. Sorry, I lost you halfway through. Try again. One hot encoding. So we're talking about circuit design. Yeah, I'm a little out of my depth. I don't know anything really about machine learning, so sorry. And I didn't quite get all the question either. Yeah, maybe we can talk after, and I can do a little research offline for you. Would that be okay? Yeah, come down and talk to me at the end of class. Okay, 2 questions. Sorry, I couldn't help the second one. Any others while we're paused? Yeah? Okay, so the thing that we're interested in dealing with these things are the distributions. And there's going to be several different distributions that you're going to be responsible for knowing a lot about. and how they behave. And the reason that we're doing this is because we're actually going to step away a bit from the sample space and probability idea. It's not that experiments aren't useful. Okay, we need to design an experiment to gather data and do our analysis, but they often give us similar pictures. Okay, so they often give us random variables that are similar to other random variables, and in so doing, we can just analyze the random variable, right? And if we know stuff about the random variable or how generally random variables behave, then we can just do that analysis and apply it to several different problems of a similar type. Okay, the main characteristics for distribution functions. Okay, so these other distribution functions are two things. One is the probability density, which is essentially a bar graph. Okay, well, it'll be rendered as a bar graph anyway of the probability of each thing in the range. And the other is a summation. Okay, so it's almost like an integral, but we're dealing in discrete space. Okay, this is known as the cumulative distribution function. It captures everything from the left up to a certain point. Okay, so I'll just read through the definition and I'll be slower about it, but that's it. And those graphs that you see for bell curves, or the things we did early with the coin tossing, where I sort of did this thing and it sort of looks like a bell, that's a probability density function. Okay, so it's essentially a bar graph of all the probability for all the possible things in the range. Okay, so it maps things onto 0, 1. If it's not in the range, it's 0. Okay, if it is in the range, then you just you write out the probability for it. And the cumulative distribution function captures everything to the left. Okay, so it's the probability that r is less than or equal to a certain value. Okay, and you'll end up getting a sort of a stepwise type function in the discrete case. And you'll typically have one or the other, and it depends on what your application is that you're going to use it for. I like to visualize PDF because I'm used to seeing bell curves and this sort of thing, and I sort of have a good intuition about what it means. Other people prefer CDF. Okay, we're going to do both today, and you'll have an opportunity to do both on your assignments as well. Let's see, some things to fill in here. Okay, clearly the sum of everything in the PDF over everything in the range, everything in the reals is equal to the same thing summed over the range, because all the things that aren't in the range have a value of 0, and this thing is equal to 1. And the CDF, being the probability of all the things less than or equal to x, is really treated as a summation of everything in the range that's less than or equal to x. Okay, so you can sort of add up all the pieces. Okay, so CDF sub r of x is equal to the summation of everything that's less than or equal to x in the probability distribution, and that's equal to the PDF. Okay, so let's finish off today by drawing some graphs. And we might not get through them all today, but I have hopes. Okay, we'll give it a try. Okay, so 3 fair coins and 2 dice. We're going to finish this off. Okay, so 3 fair coins are tossed. C is the random variable and number of heads. Okay, what's the PDF and what's the CDF? Okay, so we'll do the PDF on the left. Okay, so the PDF, we know that it follows the number of coins. It's like 1/8 for 3 heads or 3 tails, and 3/8 for 1 or 2. Okay, as a function, so the PDF of C of x is 3 choose x, because x of those coins have to be heads, the other ones have to be tails, divided by 2 to the 3, okay, divided by 8. Okay, so if we draw this on a graph, now we're going to have, well, this is 0 here, okay, so it's going to be one thing, and then let's make sure we have enough room, so that'll be 1, that'll be 2, and that'll be 3. Okay, so I'm going to draw like, bars. Okay, they're basically just points, but to make them really clear on the map, I'm going to draw lines that go up. Okay, so how far up do we go? Well, let's just say this is 1/8. Right, and that's going to go up here as well. 1/8. 3/8. This will be up here, right? So it'll be 3/8. And this one will go up. Okay, and if that's not visually appealing, and I don't think that. Thank you. I don't think it's terribly visually appealing. I sort of like to put some heft around these things, and you sort of start seeing more of a curve type of thing. Adds a little bit of area to this. Okay, but it really is a discrete function, right? There's no continuity here. Right? It's 0 everywhere else. Just got these points. Okay, the CDF, well, it only starts being non-zero once you get to 0, right? It actually is sort of continuous in a way, but it's got a step function sort of idea. It's discontinuous in some very discrete points, but coming in from the left, it's all 0, right? Until you trip over something that's in the range. and then you get this little bit, and I can't draw the whole thing in there because if I do that, it's going to be way off here. Okay, so we'll just do this little jump. Okay, so when you get to 0, there's this little jump for 1/8, right? And then when you get to 1, it's going to jump up by 3/8, right? So it's going to add 3/8 on there, and then it gets to 2. So between 1 and 2, it's there at a half. It'll jump another 3/8 once it gets to 2, and then say it's 7/8 until it gets to 3, and then it'll be 1 forevermore. Okay, so just to fill in what the picture is, I can't do all the things because it would get too messy, but it tops off at 1. This middle value here is 1/8 plus 3/8, that's a half, and that value there is 1/8. Down at the bottom, I'll put 1/8. Okay, so the sometimes I ask you for or sometimes whatever, they give it to you as a stepwise function, as a piecewise function. Okay, and you should be comfortable with doing this, and I know it's not all that comfortable in calculus to write a function that's not analytic down, but it's perfectly legal and it's very common in this thing. Okay, so to write out this function here, it'll be there's 1, 2, 3, 4, 5 pieces. Okay, so it's 0 if x is less than 0, and it's 1/8 if x is between 0 on the bottom end and 1 on the top, but not equal to 1. Because as soon as you get to 1, it jumps up to a half. So it's a half between 1 and 2, but not equal to 2. And 7/8, I guess. 7/8 between 2 and 3. And 1 if x is greater than 3, or greater than or equal to 3. Is it good? Okay, questions about this one? Yeah, so the question was, is the CDF analogous to an integral of the PDF? It is, but we're in discrete land, so if you take an integral, it's a little bit hard to do that, getting a zero integral, because these points have no area, really. But so there's discrete statistics that goes on as well. Sorry, continuous statistics that goes on as well, and it is integrals for those functions. So I'll probably mention some of that at the end of the course. But yeah, so here it's like a summation, but it's analogous in the continuous case to an integral. Thanks for that one. Other questions? Should we do the second one? I think we have time. Yeah, we probably have time to do the second one, and then we'll save the max value for Wednesday. All right. Okay, so 2 standard dice are rolled, and R is the sum. Okay, so the values here, and I want to make sure that I can fit them all in. Okay, so there's 0. That's not possible. There's 1. Okay, so there's 2, and there's 3, and 4, 5, 6, 7, 8, 9, 10, 11, 12. Maybe I could have afforded a little bit more space, but that's okay. Okay, and there's only one way to roll a 2, right? The probability is 1 out of 36. And if I was to draw this to scale on the on the x-axis, then it would be like this tiny, and it would be very useful to see. Okay, so I'm going to draw it like it's actually the same size. Okay, so this is 1/36. Okay, and this is 2/36, then 3/36, then 4/36, 5/36, 6/36, and then 5, 4, 3, 2, 1. Okay, and as so just to give us a perspective of what's going on here, this is 6/36 across there. That's 3/36. Okay, and you can draw the bars around here. I like those. It's fun, and it sort of looks like the bell curves that you see. They're Gaussians, so that's cool. Shade those in. Whatever speaks to you. That's fine. Okay. But it goes up and it goes back down, so it's got this sort of pyramid sort of thing, triangle. Over here, adding all of these things up, right, again, we start at 0. Okay. And I'm not going to write out this function because there's so many pieces to it. There's like 12 pieces, so it'd be too long, but we're just going to draw it. Okay, and it starts off, well, maybe I should draw where it finishes, okay, just to make sure I don't get too far out here. Okay, so there's 1, there's where it stops, and here's a half, okay, just to orient ourselves, so that I'll orient myself, because I tend to get a little bit out of scale when I'm drawing these things by hand. Okay, and you can see my half has already gone about half there, but anyway. Okay, so we add all these things up, so we get to 2, and there's like 1/36, and it's very thin. And then we get, we add 2/36. And then we add 3/36. That's probably too much. And then we add 4/36. And then we add 5/36. I've probably overdone it already. not too far off here. Okay, so this is where it goes to, and then 636 is where it crosses over. Okay, so 636 up here, and then another 536, 4, 3. I've sort of blown it, but I'm close. All right, close enough. So that should actually be hugging the 1 line there. Okay, so maybe I got a little enthusiastic through here. Okay, but note that this thing is symmetric. So half of this probability distribution is to the left of 7, and half of it is greater than 7, except for the stuff that's on 7. Okay, so it sort of makes sense that when you cross from, so this is 6 right in here. Okay, so that's 6. When you cross from 6 to 7, you go from less than 50% to greater than 50%. And that just makes sense by symmetry. Okay, so it sort of passes like the sanity check. Okay, so apologies. I have a remedy for this. That's to bring out the thick marker and just kind of do this. Okay, so clean that up. All right. Okay, but yeah, you can probably do better with graph paper and a ruler than what we're doing here, and you'll have your opportunity on coming assignment. I promise. Okay, so feel okay? Yeah, feels kind of intuitive. Okay, so good pictures. Okay, any questions about this? I know it's a lot of definitions, and we eventually got to a couple of examples of pictures. We have one more example to do, but we don't have enough time for it for today. So I think we'll just end it here, and this will be where we start on Wednesday. Okay. Thank you. Have a good one. See you Wednesday.